So, we shall begin with the definition of modules. You must have seen vector spaces over a field. This is exactly the generalization of vector spaces over fields to the case of objects over rings. So, in our situation, in general, one can define what is called a left module, a right module, and so on, because your ring need not be commutative. Okay. We will not go into those details, we will stick to commutative rings, and hence the definition involves only modules. Left modules and right modules are all the same. So, let A be a commutative ring with identity. A set M with a binary operation is said to be an A module if what should be the conditions? I said it is a generalization of vector spaces into the case of modules. So, what should be the conditions? The first is the intrinsic property that this should be an abelian group. And then there are interactions with the ring, okay. That is, there exists a map A cross M to M with, so A comma M going to A M map such that what are the properties that are essential? Yeah, it should be distributive over the summation A M1 plus M2 should be equal to A M1 plus A M2. Then if I take A plus B multiplied with M, it should be A M plus B M, and the associativity of multiplication, that is A B multiplied with M is same as A multiplied with B M. Okay. Yeah. Huh. 1 dot M is M. So, this for all M, M1, M2 in M and A comma B in A. So, these are basic properties that needs to be satisfied. Let us look at some examples. What should be the 0th example? Yeah, if you take any ring and take M to be 0 is an A module for any ring A. Then as I said, this is and you can see that it is a generalization of vector spaces into the case of rings. So, if you take any vector space over fields, they are all modules, A modules, F modules. Now, can you think of start with the ring A, can you think of an M? Yeah, M equal to ideals, an ideal of A. If you take a subring, yeah, if you take a subring which is not an ideal, then it need not be a module, it need not be closed under this map, might not be there. For example, if you take subring kx square of kx, right, if you take kx square and kx, then kx square is not a subring with respect to the standard multiplication. Okay. So, but if you take any ideal of A, in particular the most trivial example is M equal to A itself. Every ring is a module over itself. AX. If you take A, any ring, this is an A module. With the standard addition, multiplication and so on. What more can you think of? If I take any, if you take any ideal, so given a ring, what are the possible ways of constructing new rings, right? One is subring, then adjoining a variable, another way is taking quotient. So, if you take A mod I, this has a natural, this is certainly an abelian group, okay, and it has a natural multiplication coming from A, right. This is an A module. So, how do you define scalar multiplication here? A times x plus I is Ax plus I. With this scalar multiplication, A mod I is an A module. A to the power n. So, if you, I will come to the direct sums a little late. Another important example, which is if you do structure theorem of finite abelian groups, there is a very nice example that comes up there. Well, this is one way to look at it. So, take a vector space, let V be a vector space over a field F. Then there exists, linear operators. Let T from V to V be a linear operator. Okay. Then you can make V a module over Kx. So, take a polynomial P of x in Kx, sorry, F. Yeah.
But we already said that vector space is a module over a field.
Module over a field. Okay. Now, what we are going to do is we are going to define a module structure for V over this polynomial ring. I have to define a multiplication. Can you think of a multiplication here? So, I want for an V in V, can you think of a definition for this? Coefficients. So, what?
Summation AI V xi.
So, how does the degree, or how do you say that it is linear? Can you say that it is linear? This is P of t acting on V. Okay. So, with this you can say that with this scalar multiplication, V is a kx module, a fx module. Now, fx is when you want to study this diagonalization and the Jordan canonical forms and spectral theorem, etc. One can, there is an approach through this. For example, you can view V as a fx module, use structure theorem of modules over PID to get a specific structure for V, and use this multiplication to get, so to say what T, I mean specific decomposition with respect to T and so on. Okay. Yeah.
Sir, what is the problem if we multiply V with the every coefficient of that?
So, you are saying if Px is equal to summation ai x power I from 0 to n, then Px V equal to, you are saying ai Vi. Is that what you have? ai V?
AI V xi.
No, you have to define a map from fx cross V to V. Okay. Yeah. Okay. So, let us we will see more examples as we go along. First, let us look at some properties of modules. So, as in the case of rings, first we will look at submodules. What would be a submodule? Sorry, I forgot to include one another important example here. Let me.
This map also works for the
Associated.
Suppose, for example, if you take P1x, P2x, sorry.
through the identity operator.
Yeah, this will, yes, this is, yeah, this works. This is a special case of what we discussed here. Yeah, this is, yeah, that's an arbitrary T, and this is for identity operator, this works, correct. If you take, this is another important example. If you take any abelian group, Okay. So, for a set to be module, you need it to be an abelian group. So, start with an abelian group, then you can have a module structure on G over Z. Then G is an Z module via the scalar multiplication what should be the scalar multiplication? How do I define that? N times G. Yeah, what are the operation here is so let me write as G plus, okay. Then G plus G n times. So, any abelian group is also a Z module. Now, what should be submodule? A submodule should be a subset with
Operations of the
yeah same as operations same as in the case of module M, and it itself yeah that itself should be a module. So, a subset n of M is a submodule if n is a module is an A module with respect to the same addition and scalar multiplication defined on M. Okay. And you have a subset with the same structure remains the same. So, some examples, if you take any subspace over a vector space, it is a submodule. Similarly, yeah, take any ideal, if it is an ideal, then any subideal is also a submodule and so on. We will see a lot of examples. A map F from so let us start by saying let M and N be A modules. A map F from M to N, this is an A module homomorphism if what should be the condition? It should be a abelian group homomorphism to start with, or in other words f of M1 plus M2 should be same as f of M1 plus f of M2. Then yeah, f of AM should be A of f of M for all A in A, M, M1, M2, and N. Okay. Sorry? Do we have to specify that? Yeah, we do not have to specify that because it is already there in M. There is no f of 1 there, and both of them are modules over A. Yeah, some examples. Okay. So, what should be the 0th example? If you take any two modules m and n, if m and n are any two modules, then the 0 map is a homomorphism. So, I will henceforth only say homomorphism. It means a module homomorphism, or in the context of rings it should be a ring homomorphism. If needs to be specified separately, I will do that. Otherwise, it is the default homomorphism in the default setup. Some homomorphisms from Z to Z. Can you give me some homomorphisms from Z to Z? Identity, yes, but more. Sorry, f of n equal to minus n, yes, n equal to m times n fix. Will this be a module homomorphism? F of n1 plus n2 is m times n1 plus n2, which is mn1 plus mn2, and f of some kn is mkn, which is k times mn, which is k times f of n. So, this is a module homomorphism. Can we say something more in this? Suppose f from Z to Z is any homomorphism. F from Z to Z is Z module homomorphism. Then can we say that it should be of this form? How do you say that? If you take f of 1 equal to n, so let us use m for some m, then what should be f of any k? F of k, I can write it as f of k times 1, which is k times f of 1, which is kn, km, yeah. So, therefore, this is precisely of this form, which means any homomorphism from Z to Z is of the form Fn equal to Mn. Okay. Some more examples. A is R and M is C1 AB and N is CAB and F going to F prime. Is that what you have in mind? Yeah. This is a, so more generally any vector space homomorphism should be a modular homomorphism over the same field and so on. Now, there is suppose you fix two modules M and N, let M N be a modules and look at all the homomorphisms from M to N, collection of F from M to N. F is a homomorphism. F is an A module homomorphism. Okay. What can you say about this set? Is this familiar? For example, in the case of fields, if you take A to be a field and M and N be vector spaces, then this is denoted by L M N, right, set of all linear maps from M to N. That is also a module over, or in the case of fields, that is also a vector space over the ground field, right. So, here what do we expect? That this is also an A module. So, what should be the addition and scalar multiplication? We have to first say that this is an abelian group and then say that there is a scalar multiplication which makes it an A module. So, if I have f comma g in home A m comma n, then how do I define f plus g? F plus g should be a homomorphism which takes any m to f m plus g m. It should be, see, if you restrict your ring to a field, this should be set of all linear maps. So, you can take the inspiration from there, right. And similarly, how do you define alpha of f in or A in A? A of f is the homomorphism that acting on any m should give you A of f m. With this addition and scalar multiplication, home A m n is an A module. Okay. So, therefore, let us come back to what we showed here. What is home of, if I take home Z Z, what did we see here? It is any f has a unique integer, and also any n, given any n, I have a homomorphism. Or in other words, there is a one-to-one correspondence between home Z Z to Z. Now, what we need to check is that whenever you define a homomorphism, you have, whenever you define a map, the first two concepts involved, related concepts involved are whether the map is injective, surjective, or both. When they are both, it is called an isomorphism, right. So, in the case of module homomorphisms also, a module isomorphism is a module homomorphism which is both injective and surjective. So, first let us define those terms. A module homomorphism is an isomorphism if it is injective or one-to-one and surjective onto. So, one can see that home A Z Z to Z, there is a map f going to, can you exactly define what the map should be? F of 1, right. So, exercise that this is, so let me call this map phi. Phi is an isomorphism. You have to show that this is a homomorphism first. Z module homomorphism. So, we were yeah, A is Z. Yeah. First you have to show that it is a homomorphism. F plus G will be mapped to F plus G acting on, which is acting on 1, which is F acting on 1 plus G acting on 1, which is same as phi of F plus phi of G. Similarly, I mean some n times F will be n times F of 1, which is same as n times phi of F. So, therefore, this is homomorphism, and verify that it is both injective and surjective. So, this is an isomorphism. Now, can you see this concept in a more general setting? Okay. So, let I will put another exercise. Let A be a ring and M an A module. What is think about it, try to arrive at an answer. Okay. So, when I say what is, if you have a very specific answer, find a specific map, homomorphism, isomorphism, whatever possible. Okay. Think about this. Now, suppose I have a map f from M to M prime, A module homomorphism. Okay. Then we have two modules, right, home A. So, and N be an A module. Okay. Then I have two modules, home A M N and home A M prime N. Can you see some interaction between them? I mean, can you see some maps between these two modules? Yeah. So, I have a map from M to M prime. Suppose I have a map from M to N and I have map from M to N. So, if I have a map from M prime to N, then composing with F, I can get a map from M to N, right. That is, given an element here, composing with this, I have an element here, or in other words, I have a map from here to here. So, if I have a map, if I take a homomorphism, let us say H here, H, then look at F composite H. this will be a map from, it will be a map homomorphism from, it is a composition of two homomorphisms, this is again a homomorphism. This will be a homomorphism from M to N.
Sir, actually take M dash to N, right?
Yes.
So the domain of
I am sorry, I wrote the wrong direction. H composite F. Look at H composite F. Okay. This will be a map from M to N. That means, given a homomorphism here, I get a homomorphism here, or in other words, I have a map from here to here. Okay. So, then there exists a map phi from here to here defined by phi of H equal to H composite F. Okay. Prove that phi is a homomorphism. Straightforward verification, I will leave it to you to do that. We will study more properties of this little later. So, one, you know, there are these questions like, depending on the properties of F, how we can derive properties of phi. For example, if F is injective, can we say something about phi? If F is surjective, can we say something about phi? If F is an isomorphism, can we say something about this, and so on. Okay. So, therefore, we will come back to that little later. In the same manner, so this is one way. Another home module associated with this would be home A N M and home A N M double M prime. Again, can you see a map between them? So, now I have a map from N to M and N to M prime. So, I have map from N to M, N to M prime. Can you see some interaction? Given a map from N to M, I can compose with F and get a map from N to M prime, or in other words, I have a map from here to here, phi of H equal to F composite H. Right. So, in both cases, you should verify that this is a homomorphism. Now, suppose I have, is this clear? Are the maps clear? Yeah. Now, suppose I have a submodule of M, then as you must have done for the case of ideals, for groups, ideals, vector spaces, etc., you can define an equivalence relation X, define a relation X equivalent to Y by if and only if X minus Y belongs to N. Okay. Then this is an equivalence relation You must have done that for groups as well as ideals. And this equivalence relation gives me a set of equivalence classes. So, the set of all equivalence classes is denoted by M mod n. So, this one has a natural module structure on this, then M mod n is an A module with M1 plus n. Okay. So, this is slightly different, this plus this is a notation for an equivalence class. So, let me just write M bar. So, I am looking at equivalence class of M plus equivalence class of n. I define the sum to be equal to equivalence class of M plus n. One has to see that this is well defined. Okay. The well definedness etc., the procedure is exactly same as in the case of groups and ideals that you have done. So, I will not be going through that again. A dot M bar is same as A M bar. Verify that these definitions. So, I should do like this. These definitions are independent of the representative of chosen for equivalence classes. Basically, these are well defined. The addition and scalar multiplication are well defined. Okay. So, this is if you take any module and a submodule, you have this quotient module M mod n. Okay. Now, first isomorphism theorem, as in the case of groups and groups, rings and vector spaces and so on, we have if I have a map f from M to n be an A module homomorphism, then I have definition for kernel. Kernel of f is defined as all x in M such that f of x is 0 and another notation is image of f. This is set of all f x, x belongs to M, or you can say a set of all y such that there exists x in M with f of x equal to y. The first isomorphism theorem says what should be the first isomorphism theorem? image of f is isomorphic to quotient kernel of f. Yeah, before this one more remark. That kernel of f is a submodule of M okay. And what can you say about image of f? Image of f is a submodule of N. There is one more definition. Co-kernel of f is defined to be n mod image of f. Okay. So, now f is injective if and only if kernel f is 0 and f is surjective if and only if co-kernel of f is 0. Okay. So, these are this kernel f is 0 if and only if f is injective. This you must have seen in the case of rings in groups, rings, vector spaces and so on. This is a very strong property that that holds for homomorphism. In general, if you want to check injectivity, you have to take two arbitrary points. If their images are same, then you have to prove that these 2 points are same. But in the case of these structured maps, that is maps which preserve the structure, you only have to check whether an arbitrary element is mapped to 0 or not. So, we will continue later.